Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Deanna Hooper, Charlie to friends, and I'm a theoretical physicist currently doing a postdoc over in the University of Helsinki in the Helsinki Institute of Physics. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how things evolve, how things interact, cool stuff happening inside the universe. I love being a scientist, I love being a cosmologist, and I really like chatting to everybody about all of the cool things I get to work on. So for anyone who doesn't yet know, Cup of Cosmology is an interactive stream. The idea here is that you people can ask me anything you want about space, about physics, about cosmology, about Finland, about myself, about my cats. Obviously, I will not have all the answers, but I will do my best to answer as many questions as I can. This means that you will decide what we talk about. There is no script, there is no plan. It's up to you all where we go for the stream. So if you're a first-time viewer, welcome. Stay for the chaos. If you're a regular, welcome back. Great to see some people already coming in the comments. Mita, Scott, David, great to see you all. As always, great to see that you're always still here, ready to ask questions and ready to jump in. Love to see everyone coming back. So, Cup of Cosmology has been away for like 4 or 5 weeks. It's been an extended break that was not completely planned. Like the first weekend was planned because I was away for Easter. And then after that, it just kind of spiraled. My last 4 weeks have been incredibly busy, but overall for good reasons. I've just been doing a lot both in my private life and at work, which has meant by the time Sundays come around, I'm just exhausted. And then I don't have energy for live stream. Oh, I'm out doing stuff on Sundays. So I know it's been 4 or 5 weeks since the last live stream. So I appreciate all of you coming back and bearing with me when I take these extended unannounced breaks. But Cup of Cosmology is back today. I cannot guarantee next Sunday yet. should be online next Sunday, but I might be off somewhere. I don't. Back today. Schedule will be if and when I can manage, which is also why you should absolutely subscribe to the channel if you haven't done so already, because then if you click the notification bell, you can get notifications before I go live. Usually the streams are posted, or the live stream appears on YouTube about 6 hours before I go live. So if if about 5 hours before I'm set to go live, if there's no live stream, you can kind of assume that I'm not going to be live. But yeah, the easiest way to make sure you never miss a live stream is to subscribe to the channel, and then you'll catch all future ones because you can get notification. I see we have a couple more regulars here. Lethargo, Prath, Paul, great to see you all, as always. Indeed, it has been a long time, no stream, but today we're back. I have no idea when the next stream will be, probably next Sunday, but there's also a 2-day event that I want to go to next weekend. We'll see. Yeah, all good here, Prath. Thank you for asking. It's just been really busy the last couple of weeks for me, but good things. I'm having a lot of fun. I'm going to a lot of events. I'm doing a lot of stuff at work. It just means that the last 4 weeks have been a constant. And as a lot of you know, I am chronically ill, so I do have to take some rest days, and it happens that Sundays is usually the only day of the week that I can actually chill. So then I often have to cancel the live stream. Going forward, I am considering potentially changing my live streams to be on Saturdays. But realistically, I'm much more likely to have an event and be out and about on a Saturday than on a Sunday. So maybe we just keep Sundays going for now. As Paul is saying here, the more you do for notifications, likes, and so on, the more likely YouTube is to get new people coming in. So please do press all the buttons, like, leave a comment, subscribe, say hi here in the chat, share with friends. And if you're on Twitch, there's also buttons you can press to make stuff happen. Never sure exactly which buttons do what on Twitch, but y'all can figure it out. Press button, see what happens. Worst case, you break something. I've also realized that my camera is off today, and I'm going to very directly blame my cats for that, because one of them knocked into my laptop screen or my computer screen the other day, and now the whole setting is a bit off. I seem to be kind of centered in the image now, so close enough. Let's go with close enough. Okay, so enough babbling. Let's get into some science. Now, as advertised, Cup of Cosmology is an interactive stream. This means that it's up to you all to decide what we talk about today. You can ask me anything you want about space, about physics, about cosmology. Really, this is an open ask me anything. Depending on your questions, we decide what we end up talking about, which means you have a lot of input in deciding the direction of the stream. However, if there are no questions, I get to talk about my favorite things in the universe, as you'll know what that's going to be. It's going to be the default ones. No tariffs on Finland to my knowledge, but hard to keep up. But yes, I've just been busy. No, just been busy. That's why there's been no streams. Also been investigating another potential avenue for science outreach, but I'm still waiting to see how that's going to work out. Okay, coming from Prathia, you're usually way too out on Saturdays to drop in, so you hope the streams remain on Sundays. Yeah, I feel like Sundays is more likely to work for most people. Saturdays, most people have plans. I probably have plans. I could do it one day during the week, but I feel like that makes it a lot more complicated, especially because we operate across many different time zones. So if I did it in my evening during a weekday, most of the people based in the US, which apparently is most of my audience, would be working or during standard work hours. So I feel like Sunday really is the only day that makes sense. And yeah, I just gonna have to accept that I'm gonna be very busy some days and not necessarily on every weekend. But hopefully gonna be back a bit more frequently because the last 2 or 3 months it's been very quiet on the stream side, mainly because my life's been very busy. But yeah, I think sticking to Sunday might make more sense. Let's see. So there's a new app that I am checking out in terms of science outreach. It is called Merle, as in meet in real life, MIRL. It launched 3 weeks ago. It is an app where you can meet experts and ask experts questions about basically anything that they're experts in. It is an app that I've been kind of looking forward to for about a year since they pinged me and asked if I wanted to join the advanced program. But for me at least, the app crashes literally every time I open it. So it's still a work in progress, but if you all want to check out a new app, Merle, Meet in Real Life, MIRL, check it out. You can find my incomplete profile there and a bunch of other experts talking about random things. Still not 100% sure how I feel about the app, mainly because it crashes every time I open it. But I think my phone is old, so that's something that we can figure out. But if you want an app recommendation, I'm not sure if I'm recommending it, just check it out. You might find me there someday. Okay, seems like the general consensus here is that Sunday is better for you all in the comments. So we will most likely stick to Sundays, just accepting that I won't be on every single Sunday, but I will try to make it every Sunday that I can, bearing in mind that I obviously do not want to burn myself out. This time last year, I took on way too many things and spiraled with my chronic illness, and I ended up having many medical issues last year, partly because I wasn't resting enough. So this year I'm taking care of myself, which is always an important thing to do. Okay, so it's been a while. Let's maybe jump into some things. I'm a cosmologist. I say I'm a cosmologist. So what does that mean? What is cosmology? What is the difference between cosmology and astrophysics? Or cosmology, astrophysics, and astronomy? Excellent questions. So cosmology is the field of science that studies the universe. This means that we study the whole system that is the universe. So I study things like the components of the universe, the age of the universe, things that would help us understand how the universe evolved, what's happened over the last 14 billion years of cosmic evolution, things like this. And it is very closely related to astrophysics. Astrophysics is also studying stuff in space. The big difference here is that astrophysics is usually the things inside space, whereas cosmology considers the universe as a whole system. Now, of course, there is a lot of overlap because if you do something like black holes are stars that have reached the end of their lifetime and collapsed. It's a very massive or very dense thing that attracts everything gravitationally. So black holes are something that are small objects. They would be considered astrophysics, but also the whole way that black holes form and merge and play a role in the formation and evolution of galaxies leans a lot into cosmology. So there is a lot of overlap between cosmology and astrophysics. And often I will say, oh, this project is more astrophysics, this one is more cosmology. And then you also have astronomy, which is the study of objects in the night sky that are relatively close and can be seen from Earth with different types of telescopes. Again, there's a lot of overlap between astronomy and astrophysics. The kind of key difference is the scales on which we're working, the size of the objects we're considering. You can think that astronomy is kind of within our galaxy or close by galaxies. Astrophysics is broader, looking at different galaxies, different objects in the universe. Cosmology is taking a step back and looking at the whole system and asking questions of how does it all fit together. So there is a lot of overlap. But yeah, I'm a cosmologist. I study the universe. My specialty, my focus is the early universe. That means I focus on what happened in the first couple of minutes or even couple of seconds or even the first second of the universe, and how does that help us understand what is happening today. It's a very, very cool topic, and it means I get to study random things that we may or may not ever be able to measure. That's very cool. I see we have a bunch of questions here, and then I'll continue rambling about cosmology. Question from Paul. Have you run into US colleagues impacted by the government cutbacks in research grants and funding in various US schools? So I think this is something that is affecting researchers in the US and also has an impact on researchers across the world in general. There is a situation where a lot of grants are being cut, where a lot of people's funding is being cut. I have not noticed an impact directly on my colleagues because all of us are European based, for now at least. However, there's now kind of a push to not organize conferences in the US. A lot of people are kind of reluctant to organize a conference on a physics meetup in the US, especially given that it is, for a lot of reasons, no longer a safe place for people with different backgrounds. It's also there's the kind of risk of being deported or not necessarily having the right documentation. So there is a push now to move conferences away from the US to other countries. But of course, the US is not the only country with issues. There are other countries with a lot of problems and a lot of issues. So we do see some impact anytime science is affected in one country. It does have a knock-on other countries. I don't think I have personally been affected by the things happening in the US, nor have my direct colleagues, but I am in international collaborations, and we are there seeing the discussions about how to potentially move research outside of the US. But that is a good question. Given the current climate, it is good to consider how does this affect science. And one of the biggest impacts I've seen is people wanting to shift away from organizing things in the US. Okay. I'll answer the off-topic question from James here, and then I'll go to the physics questions that were up above. Question from James here, wondering if you were ever able to get to St. Petersburg before the recent troubles. No, I have never been to Russia. It's on. I would like to go there someday. I genuinely would like to go there. I think I moved I moved to Finland in September 2021, which is kind of recent. So even though Russia is right next to Finland right now, traveling between the two is not as feasible as it once was. I have not had the chance to go to Russia, but someday I would potentially like to. But no, I've never had the chance. Okay. Yeah, there is a comment here from Lethargo about preserving data that is currently in the US. This is, I think, a big point of concern for a lot of people, that a lot of scientific data is stored on US servers. And if there are ideas to kind of cut this or modify it or remove all of the bad words from data, which doesn't have such a big impact on the type of data we deal with, but is still something to consider, there is a big push to move some data and some servers and some things, or at least back them up somewhere that is not the US, just in case they get lost or they get deleted, because their longevity can no longer be assured if they are kept on US servers. So there is a big push to move a lot of astronomical data, a lot of space data, or at least not necessarily move it, but at least back it up somewhere that is less likely to run into issues in the next couple of years. So that is something that people are looking at as well. Okay, so there was a question here from David Howden. Do I recall rightly that you can think of the whole universe as being a black hole? If so, will it evaporate? Excellent questions there. So a black hole, as I was saying before, is a region of the universe that is so incredibly dense that nothing, not even light, can escape. In order to escape the gravitational pull of a black hole, you would need to be traveling faster than light in a vacuum. As far as we know, nothing in the universe can travel faster than light in a vacuum, and therefore nothing in the universe can escape the gravitational pull of a black hole. Now, I've just realized my camera's still too high because you can't see all of my hand gestures. Not that I'm doing anything interesting, I just like waving my hands around wildly. And now you can't see the calendar, but now I'm kind of more in view. Yeah, this feels right-ish, approximately. Oh, good enough for our intents and purposes. It doesn't need to be perfect. Yeah, so black holes are incredibly dense. You would need to travel faster than light in a vacuum in order to escape a black hole, as nothing can travel faster than light in a vacuum. To our knowledge, nothing can escape a black hole. So we know of several different types of black holes. There are the stars that reach the end of their lifetime and collapse to form black holes. You can also have supermassive black holes, which are the ones that we believe exist at the center of every galaxy. And you can have something called a primordial black hole, which is a hypothetical type of black hole that would form in the very, very early universe when a region of space-time is so dense it can automatically or directly collapse to form a black hole without going through the whole stellar evolution process. Now, one thing that we can think about with a black hole is the so-called event horizon. Now, the event horizon of a black hole is what is known as the point of no return, or the kind of the point where the black hole begins. So if you're away from, I'm just going to grab my black hole prop because I have a black hole prop if I'm not going to use it. This is my black hole. It has an accretion disk around it, matter spiraling around and falling into the black hole. At this point here, this is what we call the event horizon. Anything outside the event horizon of a black hole can still escape the gravitational pull. If you're passing around here, you will be deflected by the black hole, but you won't necessarily fall in. Once you cross the event horizon, this line here, there is no coming back. At this point, you cross this event horizon, you fall into the black hole, there is no escape. At that point, the gravitational pull is so intense, you cannot get away from it. So the event horizon is kind of the border of the black hole, the point from which there is no return. Just going to mute myself 1 sec because this feels like there's something in my throat and I don't want to cough on you all, so I'm just going to mute 1 sec. Okay, that did not in any way help, but at least it felt like it did. I know I've kind of been hermiting at home for the whole weekend because of a busy week. I actually haven't really talked to anyone, and I think my voice now is just like, oh no, not doing it. Okay, so yes, you have a black hole. This is the event horizon of a black hole. Now, mathematically, when we calculate the event horizon, it's the point of what we call causal contact. Because this separates things inside and things outside, things inside cannot impact things outside. They're no longer in contact with each other, separated by this event horizon. Now, our universe also has a kind of equivalent to an event horizon. Our universe is massive, it's infinitely big. But if we consider the observable universe, the patch of the universe that we have access to, we can define a kind of horizon around the observable universe, which the observable universe is everything in the universe that may have at some point had contact with us. So it is completely determined by the speed of light. If you have a universe, an observable universe, it's basically everything that theoretically has had time to exchange information with other parts. The observable universe is centered around each individual observer. So we are not the center of the universe, but we are the center of our observable universe. Now, mathematically, this boundary of the observable universe, again, when we talk about the whole universe, there are no boundaries because the whole universe is infinite. But when we talk about the observable universe, there is this boundary around it. And mathematically, this boundary around the observable universe behaves the same way as an event horizon. This also means that we have no causal contact with anything beyond this radius or this border of the observable universe. Anything inside we could hypothetically see someday. Anything outside is inaccessible to us. Now, again, I'm talking about the observable universe and not the whole universe. The whole universe is infinite. There are no borders. There are no boundaries. The observable universe is not limited by the technology and what we have been able to see. It is limited by what has been able to send us information. By construction, this kind of means that it is the limit, or it is a limit given by the speed of light, which is also very true for the event horizon of a black hole. The event horizon of a black hole is determined purely by the black hole mass, the black hole radius, and the speed of light. And once you have those three things, you can, and the gravitational constant, which is something we know and we've measured. So once you have that, you can define the event horizon. So even though our universe does not really behave like a black hole, from an outside perspective, each individual pocket, each individual observable universe, again, there are an infinite amount of observable universes because everyone in the universe will have their own observable universe. But if you could somehow remove yourself and look at the bubble that is our observable universe, you could very easily interpret that as being a black hole. So just because the way the event horizon is defined is the same way that the boundary of our observable universe is defined. So going back to the question that we had here, that this is a long-winded answer to, the question from David Howden was, do I recall rightly that you can think of the whole universe as being a black hole? No, you can think of the observable universe as being a black hole, but not the whole universe. The next question is, will it evaporate? So even though nothing can escape the gravitational pull of a black holes have a very cool thing where you can have something known as Hawking evaporation or Hawking radiation. So the universe is continuously producing particles and destroying these particles. So you can imagine the universe has a baseline amount of energy, which we call the vacuum energy of the universe. Now, sometimes you can kind of borrow energy from the universe to create two particles. These are virtual particles. They don't really exist for long, but they just pop into existence. You create a particle and an antiparticle, which is the particle's opposite. These immediately meet, they annihilate, they release energy, and they return the energy that was borrowed from the universe to produce these particles. Now, if you produce a pair of particles anywhere in the universe, they immediately they meet, the particle and the antiparticle go away, problem solved. You borrow energy, you produce two particles, you destroy them, you get back the energy. However, what happens if you pair produce two particles right on the event horizon of a black hole? So if you produce two particles right here, what can happen is that due to the gravitational force, one falls in and the other goes out. So even though this is not escaping from inside the black hole, it is something that is produced on the surface of the black hole. I'm using quotation marks here because you can't really define a surface of a black hole, but we define the event horizon. So if you produce the particles on the event horizon of the black hole, one can fall in, one can go out. But now you've kind of borrowed energy from the universe to produce particles and you haven't given it back. So to compensate this, the black hole loses a bit of mass to kind of compensate the energy of the escaping particle. So for all intents and purposes, this looks like a particle escaping from the black hole and taking some energy with it. However, this is not the case because we know nothing can escape from inside a black hole. So what is actually happening is you're producing two particles here. One goes in, one goes out. The black hole loses a tiny bit of mass, a ridiculously small bit of mass. And this is something that we're pretty sure happens in the universe. It's something that has been a theoretical concept for many years. We have never directly observed Hawking radiation yet, but this would lead to the black hole getting smaller and smaller or losing mass. And eventually, the idea is that if it loses enough mass, the black hole itself can evaporate. It can go poof. Then the question is, what happens to the information that the black hole contained? Where does that go? That is still a bit unclear. But you could have black hole evaporation due to this Hawking radiation. Hey, Guadav, great to see you as always. Nice of you to stop by. Welcome. So the question then was if the universe as a whole can be considered a black hole, which we've already said we're not considering the whole universe as a black hole. We are considering the observable universe to be a black hole. Now the question, could this evaporate? Really feels like there's something in my throat right now. I will keep switching between my water and my tea until it clears. Okay. One sec. Good then. My cat is just deciding to use to eat this scratching post. Okay, he stopped eating the scratching post. That is good progress. So, could a black hole the size of the observable universe evaporate? The short answer is probably not within the lifetime of the universe. Now, if we consider that the size of a black hole is determined by its mass, that gives you the radius. The mass and the radius are linked. If you have a black hole the size of the observable universe, it is going to be incredibly big. We also know the energy of the observable universe. A black hole with that amount of energy or that amount of mass is extremely big. It would take many, 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 many more years than we have available in the universe for a black hole that size to evaporate. So the universe is 14 billion years old, to our knowledge, to the best of our knowledge. I don't want to do the exact calculation of how long you would have to wait, but it would be a lot more than a couple billion years in order for a black hole the size of the observable universe to evaporate. So it's not something we need to worry about anytime soon. So back to the question. The question was, where was the question? The question was, can you think of the whole universe as being a black hole? No, but you can think of the observable universe as being a black hole. And will it evaporate? Probably not within the lifetime of the universe. Excellent questions, though. And now we have some follow-up questions here about the black holes. And then I will go to the other questions that were being asked. But I said this also raises the question that do black holes in our universe have universes inside of them? We don't know. Because nothing that crosses the event horizon of a black hole can escape, we have no idea what happens inside a black hole. We have no information about what's going on inside a black hole. We're pretty sure it's not connected to a library in a time traveling kind of way, but also we can't disprove that. Once you go beyond the event horizon, we have no information. Nothing can come back. So we have no idea what is happening inside. There is the idea of we have all of this mass spiraling around and falling in. So this is adding energy, this is adding information to the black hole. What happens to all the information that falls in? Depending on how you do the math, either the information is contained inside or on the surface of the black hole in what is known as holography, all of the information on the black hole existing on the surface of the black hole. Also, this plushie was an excellent investment. I love my black hole plushie. It is super satisfying to squish the black hole as well. And it has a white hole counterpart just because it's a super cool prop. So, got distracted there. We don't know what is inside a black hole. We have no way of knowing what is inside a black hole. If you want to put down my fidget toy. If you want to imagine that there is a universe inside a black hole, this is not something that we can actually disprove in any way. However, it is not. Usually, we kind of apply the simplest ideas. So why complicate your model if you have a simple answer? Now, we don't know what is inside a black hole, but if you want to form an entire universe inside a black hole, that is a level of complexity far beyond there just being nothing inside a black hole. So that is an additional level of complexity. Sticking with black holes. I'm just going to stick with black holes and then go back to some other very cool questions that I've seen here in the comments. Comment from Scott here. What about spinning versus non-spinning black holes? I remember you saying that all the equations are based on non-spinning black holes, even though they can't possibly exist. Yeah, so we do have the mass to describe spinning black holes as well. However, it is just much more complex. So anytime we want to do simple things with black holes, we consider the case of non-spinning black holes. Now, it's quite likely that most black holes are actually spinning because it's quite hard to produce things in the universe that have no angular momentum rotation. And as soon as you have any bit of rotation, it's going to kind of keep rotating unless something stops it, assuming it has enough energy. So most black holes are considered to be rotating objects. So you're probably spinning in this direction because that's how the accretion mass is going, or the accretion disk. However, mathematically, it's much easier to consider that they are not spinning. This is the difference between a Schwarzschild black hole, let's pronounce it properly, a Schwarzschild black hole, which is one that is static, and a Kerr black hole, which does have spin. We do have the mathematics to describe both of them, but usually we think about non-spinning stationary black holes, just because it's a lot easier. Following up with black holes, James asked the question, can we have black holes with black holes inside them? I mean, if we're going down the path that a black hole has a baby universe inside, then there could also be tiny black holes inside that black hole. What would this mean mathematically? No idea. The cool thing is, inside a black hole, our maths break down, our equations break down, so we have no idea what is happening inside a black hole. Mathematically, we cannot describe it. So, could be anything. Question from Prath, where would it evaporate into? This is an excellent question. Now, if we're considering a black hole the size of the observable universe, again, this is not all of the universe, this is just the observable universe, then what it would evaporate into is the remaining of the universe, the rest of the universe. So then you could ask the question of, is there any way to measure this? If we could see other observable universes leaking into ours, what would this mean? What would this look like? What would this entail? It's cool thought experiment. So the general idea is we don't think about our universe as being a black hole. You can kind of visualize the observable universe as having an event horizon, which therefore means from the outside it could look like a black hole. However, all the observable universes are going to overlap, because if I go 100 light years in that direction, I'm going to see a very slightly different observable universe. So this is something that is not so much disjointed bubbles, but it is overlapping pockets of observable universes. But from a mathematical point of view, you can consider the event horizon of the universe. Sorry, the radius or the border of the observable universe, you can consider it to be sort of like an event horizon. Assuming the universe is flat, I should make the point that everything I've just discussed about considering the observable universe to be an event horizon is under the assumption that the universe is flat, which is, to the best of our knowledge, accurate. According to all of our measurements, the universe is indeed flat. A comment from Scott here, smaller black holes evaporate faster? Wouldn't it make more sense that bigger ones would evaporate faster because of the larger surface area and the odds of pair creation? But in order to evaporate, you need to get rid of all of the mass inside. So even if you have a much larger surface in a big one, the thing that matters there is the mass, the volume, the overall amount of energy you have in that system. So even though the surface grows, the amount of energy or the matter that you have inside is also going to scale. So a smaller black hole, even though it has smaller surface area for the pair production of particles, or a smaller event horizon for the pair production of particles to happen, the amount of mass you need to lose in order for it to evaporate is substantially smaller. If you have a massive black hole, it's going to take substantially longer to evaporate, even if you have a larger surface area on which this evaporation can take place. Whew. Okay, coming from Guadalf, sticking with the black holes, and I want to go back to the question about accelerating things in the universe, and then back from the top to make sure I didn't miss any other questions. What does black hole's entropy scale with its surface area? Why does black hole entropy scale with its surface area and not its volume? Excellent question. I'm trying to remember my formula for entropy of a black hole, and it is not coming to my brain. But yes, normally entropy, so the amount of chaos in a system, scales like the volume of a system. However, for a black hole, the entropy, so the amount of chaos, the amount of possibilities, changes with its surface, not with its volume. The reason for this is currently eluding me, but it is related to the fact that the volume of a black hole is not the most significant quantity. What we actually always talk about is the mass and the radius. So the way that black holes grow with mass is not a cube law like it would normally be in other systems. So that means that leads into the idea of all of the information of a black hole could be contained on its surface. And then rather than treating this as a 4-dimensional object, you can kind of reduce it to a 3-dimensional object, which is the 2-dimensional surface plus the time dimension. So because of the way that black holes grow, or the radius of a black hole grows in a way proportional to the mass that is different to how you would expect it to do, it allows us to treat the black hole as basically the event horizon. So the entropy can also be treated as something called on the surface surface, again in quotation marks, of the black hole, which I realize is not a very satisfying answer because I basically just said because the math says so. But that's the best answer I'm going to be able to give you right now because I'm currently not sure if I can pull up an explanation of entropy on the surface on black holes off the top of my head. But that is an excellent question, my love. Okay. Following with the black holes, question from Lothargo here: do our maths break down everywhere within a black hole, or only at the singularity if they exist? I understand that we can never observe anything to prove it. I'm just wondering about the theory. Excellent question. So we always define the singularity as being mathematically the point where things break down. Now, in a black hole, you technically have two singularities to consider. You have the surface one, which is the event horizon, and you have the one that would be directly at the center, which is the smallest point you can consider inside a black hole where everything breaks down. However, our math already gets funky on the event horizon of a black hole, but this is kind of a fake singularity in a mathematical sense. The reason being that you can put yourself in a different frame of reference, which means a different point from which you define your equations, and then the event horizon becomes less meaningful. The clearest way to think about this is if I was jumping into the black hole, diving headfirst into a black hole, not a good life plan, do not recommend it. But let's assume I'm jumping into the black hole. I would not notice crossing the event horizon. The light beams around me would change, but physically, this is something I can cross. This is a boundary I can go over. So if I was jumping into the black hole, I would not notice the event horizon because from my frame of reference, the event horizon is not well defined. So this means that it's a singularity that you can kind of escape. However, at the right at the center of the black hole, there is the singularity that is unavoidable, whichever frame of reference you're in. That is a true singularity. That's where our equations break down. But also going into the event horizon, it becomes very hard to define what happens afterwards. You can, from the outside, define it. You can define it from the point of view of someone falling into the black hole. So you can actually kind of have a different type. You can still use math to explain what happens when you jump into a black hole. We know that light would bend around, that all light cones would lead to the same place, time would get funky. We know kind of these things. So the true singularity where our math breaks down, this is a very technical question, and I love the question. So the true singularity where everything breaks down is at the center of the black hole. But physically, we don't know what happens beyond the singularity of the event horizon. So we often say our equations break down beyond the event horizon. That is not technically true. The equations technically break down right at the center of the black hole. But what happens between the center of the black hole and this event horizon is also unknowable to us. So we kind of just throw the whole thing under the singularity umbrella. But if you want to get super technical mathematically, two singularities to consider: the one at the center of the black hole, which is a true singularity, and the one on the event horizon, which is not a true singularity, because from the frame of reference of a person jumping into a black hole, the singularity of the event horizon wouldn't be noticeable. And this is a super technical question, and it's also something that we make general relativity students calculate. It's kind of like, throw someone into a black hole, what do they experience? What do they perceive? At what point do they know? Do they ever reach the black hole? Or does time slow down so much that they never actually cross the event horizon? There's a fun exercise we would set them in when I was the teaching assistant on general relativity in Aachen. And it's basically a stormtrooper falls out of a spaceship and is falling backwards into a black hole. And as this stormtrooper is falling into the black hole, they shoot 3 laser beams. One before reaching the event horizon, one exactly at the event horizon, and one once they've fallen into the event horizon. And the question was to calculate where do these light beams end up? Who perceives them when? And how would the person falling know when to shoot these light beams? I thought it was a cool exercise. I think the students who had to calculate this did not necessarily think it was a fun exercise. But these are the type of questions that we would ask in our general relativity course targeting late undergrad or early master students. Comment from David Howden here. You wouldn't notice the event horizon, but once you cross it, you cannot get back. Correct. Which suggests there is a difference to you. Not necessarily. There is a difference in the gravitational field around you, but it's not something that you would necessarily notice in the way, assuming that you are jumping into the black hole, you're already on that gravitational trajectory. So the noticeable difference would be in the way the environment around you behaves, but you're not suddenly going to hit a wall when you hit the event horizon. You're not suddenly going to be like, oh, this line here is the event horizon, I can see it coming. You wouldn't see it coming. But once you cross it, it would kind of be a slow and gradual thing that light beams would start getting more and more concentrated. And once you fall in, there's only one direction that light and space and time can travel into. And this is the thing, it's kind of the breakdown of how space and time behave. So my takeaway is don't jump into a black hole. It's not fun. And don't try to do math inside a black hole because it's also not fun. Black holes are cool. Okay. Scott is saying, trick question. The real answer is none of the blaster bolts go anywhere they were meant to because stormtroopers have notoriously bad aim. Yeah, that is not taken into account. I guess because the idea is you're not shooting at a person, you're just shooting at the ship that you fell out of. So I guess you just aim approximately. But yeah, there's a fun thing that depending if you're falling backwards when you do this, or if you're falling forward and you're shooting away from the black hole or into the black hole, the light beams behave differently. That is very cool because then it's kind of the direction in which the light is traveling adds another layer of complication. So then you can complicate it more. Like, let's say you fall into a black hole. You're falling into a black hole before you reach the event horizon. If you want to maximize the chance of someone picking up your signal and rescuing you, which direction should you fire the light beam into to increase the chances of somebody noticing it? The actual answer, I think, is if you're falling headfirst into it, you actually want to kind of shoot it just very close. Like I'm falling this direction, you kind of want to shoot it close but that way, with the idea that then it would be deflected around and come back out potentially, or just turn. Yeah, interesting to think if you're falling into a spaceship, into a black hole, and you have a laser pulse, where should you shoot the laser pulse to ensure that someone can rescue you before you reach the event horizon? Or just, don't jump into a black hole. Okay, we had a bunch of very, very cool questions about black holes. Here has been a 40-minute debate, or not 40 minutes, been a 30-minute debate about black holes. At what point do you start getting spaghettified? Excellent question, John. So spaghettification is the cool thing that, cool depending on your perspective, as you approach a black hole, the gravitational force is going to be substantially higher the closer you get. So if you were to jump into a black hole headfirst, now we're diving into the black hole, just go for it, jump into the black hole. Your head will start feeling a much stronger gravitational force than your feet. And this can actually lead to you gradually being stretched in a phenomenon known as spaghettification, because physicists are terrible at naming things. So as you get closer and closer, the gravitation, you basically have tidal forces. So the force you feel on your head is stronger than the rest of your body, so you gradually get stretched more and more. This process already happens before you reach the black hole. Also, time will slow down for you. So if I were to jump into a black hole, already as I get closer and closer, I'm going to start experiencing this spaghettification. You need to get really close to a black hole. How close depends on the mass. But once you get really close, you get the bigger spaghettification. But then there's a cool thing that if I'm the one jumping into the black hole, not only is space distorted, but so is time. So time would slow down. So technically, from my perspective, I might never reach that black hole because as I get closer and closer, time is going to go slower and slower and slower. So the black hole is gradually, even though it's approaching me, the speed at which I'm approaching it is going to feel distorted to me because of the distortion. So that's also the thing of, would an outside observer actually see you fall into the black hole because they would see time travel slowly for you? Would they see you get stuck on the black hole somewhere? So yes, spaghettification, or the process by which your head and legs get pulled apart due to the gravitational tidal forces from the black hole, would already start before you reach the event horizon. Once you reach the event horizon and you cross, you're gone. before that, you could potentially still be rescued, but you might be spaghettified in the process, which is probably not good for the human body. So yes, you can already get the spaghettification starts already before you reach the black hole and before you reach the event horizon. Already close to the event horizon, the tidal forces are going to be strong enough that you already will feel some of the initial effects of spaghettification. Whew, excellent questions. Comment from Paul here. I imagine this thought experiment will be further complicated by accepting light as a wave and not as photons. Yes, indeed. Although in our experiment here, you have a laser beam which we know emits a pulse of photons, which can be considered both a particle and a wave, but in this case, it's a clear pulse. So it's something that you can say it's traveling in that direction. It has, in this regard, the behavior of a particle or a stream of particles. Okay, comment from Scott here. According to the Star Wars canon, the blaster bolts don't travel at light speed because they're not lasers, they're quantities of charged plasma, and that's why we can't see them at all in the movies. Okay, let's assume you have a laser gun, like a lightsaber, that fires pulses, because if it's charged plasma, then you're going to have a hard time calculating things. At least we let the students assume that they were using something that traveled at the speed of light. Make it slightly easier, potentially. Okay. Guadav. Comment from Guadav here. In which direction should you fire your signal if you are falling in the black hole? Every direction possible. But what if you had a limited amount of blasters? The question is, when and where should you fire it to maximize the chance of rescue? Of course, if you're falling into a black hole, you're not going to pull out your pen and paper and start doing general relativity. Like, wait, let me figure out when to call for help. I mean, at that point, you've got bigger things to worry about. Lightsabers are also plasma. Like, technically, yes. Gonna get into Star Wars lore here. Yes, technically a lightsaber is plasma. However, it's called a lightsaber. It is a saber of light. I don't care what they want to call it. It is a concentrated light beam, which is also not something you would realistically be able to use in a fight. Lightsabers make no sense physically, but they're not supposed to. It's sci-fi. That's okay. I'm okay with lightsabers. I am not okay with a race being 12 parsecs as a unit of time when parsecs is a unit of distance. That I'm not okay with. Lightsabers I'm fine with. The Force I'm fine with. I take issue with midi-chlorians in the blood, and I take issue with 12 parsecs being used as a unit of speed instead or time instead of a distance. I know they retconned it in the future, and they're like, oh, he took a shortcut. He did the race in 12 parsecs. That's called cheating. No, that's retconning something to try to make it make sense. It didn't make sense. Okay. Paul's point of view here, you should just use the Force instead. Yeah. Yeah. I mean, if you can use the Force. But again, we were operating under the assumption that the person jumping into the black hole is a stormtrooper and not a Jedi or a Sith, so therefore not a Force bearer. Okay. Comment from Scott. I read that an observer would see them getting closer to the event horizon slowly, then the image would freeze, then they cross slowly, redshifting until it disappeared. Yeah, pretty much like that. Yes. Okay. Whew. Comment from John here. Love all the questions about gravity and about black holes. This is super cool topics. There was a question I saw before about acceleration and deceleration when thinking of the universe as a black hole. And there's a few other questions at the start that I want to get to. I have not forgotten your questions. We'll get to them. Comment from John. What do you think of the idea of quark degeneracy stars whose surface is below the event horizon? So I have on my trusty piece of paper that only comes out when I do these streams. I have a question of looking to how to explain quark confinement and quark degeneracy, and I have not looked into this. So you could have a star where there's quark degeneracy. Yes, it's a very cool question. I don't feel confident enough right now to talk about quark degeneracy stars with event horizons, but it's a cool topic, and I'm adding a note to my quark confinement, quark degeneracy plus stars to look into that, because that is a very cool question, John, but it's one that right now my brain is not going to find a satisfying answer to. But very cool question there, John. Question from James. I love that this black hole conversation is bringing up so many very cool questions and that we're all having a lot of fun with these thought experiments. Question from James. Is there a mathematical formula for how much gravity is necessary to cause spaghettification? Would the sun gravity work? Yes. It's basically related to the mass and the tidal forces. Now, tidal forces on a much smaller scale is something we're already very used to. There's something that happens when you're forming a moon, when you're forming a moon, where there's a certain limit of how far away the moon needs to be from the planet in order for it to actually be able to be stable and not be pulled apart due to the tidal forces of the planet. So there are actual limits of stability for planets around stars, for moons around planets, because these limits are kind of the limits at which structure can survive without being torn apart. And this is a very similar idea to spaghettification. It's basically how close you are to the massive object that is causing the gravitational field and the relative masses between each one. Now, usually to have a dramatic effect, you need a very big mass difference. For an example, with a planet and a moon, or with a star and a planet. If you have two planets that are similar sizes, you won't get this kind of spaghettification or these tidal forces because of the kind of similar sizes. So if you were to jump into the sun, would it be enough to cause spaghettification? I don't think so on a human. However, there's a lot of other issues like burning up. I don't think the sun would be massive enough to cause a lot of spaghettification in a human, but it might be. So I think the idea is in order to feel the spaghettification, you need to be closer than the surface of the sun. And at that point, you'll be dead through other causes. So yes, there was a mathematical formula for how much gravity is necessary for spaghettification. This is something that we can calculate the direction to go. You can look up spaghettification and you might find it. I'm not sure how close you would need to get to the sun and how massive you would, or how small you would need to be in order to feel the spaghettification. But it is not just black holes that can cause this, it's anything that has enough mass. Okay, a very cool question there, James. As Scott is saying, the Roche limit, yes, exactly. That is the limit that you need for a moon to be stable. Press, didn't I have some questions about quarks that you said you'd have to follow up on? Yes. They're written down. There were questions about how to explain why forces act differently at different distances, how to explain quark confinement. That is written down. Doesn't mean I've looked into it, but it's on my list. And I think somewhere else there was another question. Yeah, quark confinement and virtual particles on a different page. Prath, I believe that one was also yours. How does quark confinement behave with virtual particles? That one's also on my list. Yeah, I think I'm just going to have to get a QCD expert or somebody who works on quark confinement to come on the show and answer all of your questions about quarks, like all of you in general and you specifically, Prath, because there's always a lot of very cool questions about quarks that I don't feel comfortable enough answering. But yes, they are all written down. Quark confinement, virtual particles, forces and distances. Now quark confinement and quark degeneracy in stars. It's all on the list. Doesn't mean I'm going to look into it, but it's on the list. So someday I might. The sun's outward pressure would probably prevent spaghettification. Would it though? I mean, we were operating under the assumption that we were just looking at the sun's gravity, right? We were ignoring heat, we were ignoring solar flares, we were ignoring things like that. I'm not sure if the sun's pressure would be enough to overcome spaghettification. Yeah, I'm not sure. I feel like, again, you would have other problems jumping into the sun. So I'm going to do the thing I always do when I don't know the answer to a question, and I'm going to see if I can very quickly figure out the answer by looking into, by just Googling it, basically, which is a terrible idea now because the first results are all AI generated and are absolutely pointless. Let's see. So spaghettification is also known as the noodle effect. Good to know. It's the vertical stretching and horizontal compression of objects into blah, blah, blah in a strong, non-homogeneous gravitational field. No mention of it needing to be black holes. In the most extreme cases, it is near a black hole, but it could happen anywhere. So I'm not sure if it would happen on the sun. but it potentially could. You can also have spaghettification already falling into a planet. So it doesn't necessarily need to involve the event horizon. It just needs to, or a black hole. It just needs to involve something with a non-homogeneous gravitational field, so some type of difference in the gravitational field. This is something that, yes, it could happen with the sun. I am not sure if the sun's pressure or other effects of the sun would mitigate the spaghettification. But the sun is constantly spitting out particles, but it is also sucking things in. It is spitting out particles because of the ongoing fusion. So I'm not sure, would fusion be enough to counter that? Probably not. I don't know. Let's throw something into the sun and see what happens. But yeah, I think in order to feel the spaghettification from the sun, you'd need to be a lot closer than the surface of the sun, and therefore, any type of experiment we do, any probe you throw at the sun is going to burn up before you could experience a spaghettification. I think. I'm not 100% sure about this. Hey, comment from Lethargo when we're talking about the stormtrooper falling backwards into the black hole with a blaster. I like the idea that you have a blaster and a lightsaber, but have to use the laser pointer you play with your cats with as your only hope. Yeah. You're falling into a black hole. You have a lot of different things. But if we agree that your pulse blaster is not emitting light and your lightsaber is not emitting light, then yeah, get out your little cat's laser toy and shoot that in some direction to maximize your chance of survival. Yes. Maybe I should rewrite that exam question in Aachen to be like, assuming you have something that emits light that is not a pulse blaster. Hey, comment from Guadav. Question. Is there a perfect orbit that jumps about. Is there a perfect orbit just outside the event horizon where you could live indefinitely, experience extreme time dilation? Technically outside of the event horizon. Yes. Just outside the event horizon, probably not. Because if you're in orbit here, you will fall in. You can't be in orbit around a black hole. No matter what Doctor Who tells you. You can't be in perpetual orbit around a black hole due to the forces and the gravitational force and how everything is moving. You will eventually fall in. There is a point very far away from the black hole where you could be in orbit, but not close to the event horizon. So I think if you're close enough to experience strong time dilation effects, you're probably not going to be able to stay in orbit for long. However, you could find kind of an in-between ground where you can still have a stationary orbit around a black hole, but at the same time, you are starting to feel some time dilation effects. But I think if you want extreme time dilation, you won't be able to stay in perpetual orbit. If you want to stay in perpetual orbit, you won't have time dilation. There's going to be a sweet spot, not close to the event horizon, but kind of out here, where you could potentially be in orbit without feeling too much time dilation. So yes, the closer you get, the more time dilation you will experience. Okay, question from John here. These are very cool questions, by the way. I love all of these questions. We've gone really into black holes today, and that's really cool. And I love all of the kind of thought experiments you're coming up with of let's jump into a black hole, let's do this to a black hole. It's really fun. And there's still other questions I need to get to, but sticking with the black holes. Question from John here. When a neutron star eats another star and one gets stretched into lobes that spiral into the other, that seems kind of spaghettification. It is. So when you have two black holes orbiting around each other or two neutron stars, if there is a big mass difference between them, the big one can kind of rip apart the small one and gradually eat it up. This is true for neutron stars, it's true for black holes. Often what you might see is if they have similar masses, they're going to spiral and gradually collide. But if one is substantially bigger than the other, the big one can absolutely pull apart the small one and eat it up. This is also tidal forces, which means it's a kind of less extreme version of spaghettification, but it is the same process. It is this idea of spaghettification, of too much tidal force or the gravitational force on different points of a system being enough that it can either tear it apart or stretch it or pull it apart and eat it up. So yeah, this is the same kind of principle. It is the idea of tidal forces or forces that are different on different points of the body, causing either spaghettification or destruction of the system. Yeah, If you are in orbit around a black hole, as Paul is saying, it would be a lot of hazards from other incoming or similarly orbiting materials. Absolutely. Comment from Gwen out there. I might know some beauty companies interested in the answer to my question. Yeah. Do you want to live forever? Do you want to unlock immortality? Launching this year into a black hole. Launching you into a black hole this year to live forever. And not age. Nobody would see you aging if time dilation is so strong. That's how you reach eternal youth. Throw yourself into a black hole, and everyone will always perceive you as being young. Again, don't come here for the cosmetology. Come here for the cosmology. Comment from Scott here. I thought the reason for spaghettification was the extreme increase in the curvature of spacetime. No, it's kind of related. The extreme increase in the curvature is a huge gravitational field, but you kind of need the gravitational field to be different on different parts of the object to experience either spaghettification or being torn apart. The underlying principle is tidal forces, which is having different amount of gravitational force on different parts of the object. So yes, it is in essence the extreme increase of the curvature of spacetime, because gravity is just the curvature of spacetime. So you can describe gravity purely as the curvature of spacetime. So if you have a huge gravitational force enough to create tidal forces, you would also have extreme curvature of spacetime. As part of saying, you would need a gravitational gradient high enough to overcome the force that holds your body together. Yes. So this is the idea here, that the difference in the gravitational force that you feel between your head and your feet needs to be big enough to pull you apart. On this, then obviously there's some questions of human biology. How much force does a person need to be torn apart, or to just experience this spaghettification? It's kind of like the medieval stretching board taken to an extreme. Probably not a good way to torture people. I don't know, throwing people into a black hole. There's got to be more cost-effective ways of doing that. Okay, I love the jokes about finding immortality by jumping into a black hole. Cosmology's evil twin often confuses cosmetology. Astronomy's evil twin often confused is astrology. Yes, I mean, you put astronomy twice, but I'm pretty sure the second one was meant to be astrology there. Yes. Regarding quark degeneracy, going to add it to the list. In my opinion, he started off as more of a degenerate in the early days. Yes, indeed. Love the jokes, love the comments. Very much appreciating the interactions today and the energy you're bringing to the stream. You know, when I come onto these streams, I have no idea what to expect. I have no idea what kind of energy you're all going to bring, and I love it when you bring this kind of wacky, matching my energy kind of mood, where we can talk about stormtroopers jumping into black holes scientifically. Okay, there was a question some time ago that I wanted to answer back when we were talking about the universe being perceived as a black hole, and if we have the kind of boundary of the universe. There was a question from Paul. This question came 35 minutes ago, but I'm on it. Is it true that there are things in our observable universe that are not accessible due to accelerating expansion? If I were to point a laser at those objects, it would never reach. That is completely true. So our universe is currently expanding. This expansion is accelerating, which means the universe is expanding faster today than it was in the past. So even though our observable universe is constantly growing, because as time passes, there's more of the universe that we have had time to access. The light from those distant objects now falls within our observable universe. So the observable universe is constantly growing as time passes. However, we are also undergoing accelerated expansion, which means some things inside our observable universe are being pushed outwards. So you can kind of imagine the battle of the observable universe growing, but things that are kind of on the outskirts of our observable universe could eventually accelerate away from us fast enough that they would overtake the kind of bubble of our observable universe growing. So if your observable universe is growing like this, but objects are moving away from you like that, then there are some objects in our universe that are moving further and further away from us. This is also the idea that if the universe does eventually end up in what is known as the heat death, sorry, not the heat death, the big rip, or even the heat death, where the universe is expanding and this expansion keeps accelerating. It's either enough to tear the universe apart at its seams in what is known as the Big Rip, or we end up at the heat death, where everything ends up so far away from everything else that you cannot exchange energy or information or knowledge. So the universe ends up a cold, empty, dead, desolate wasteland. And I love that we cycled back to how the universe might end, because I believe that's one of the prompt questions I put in the caption today. I always come up with 3 random questions to put here, and I believe the ones today are: what is cosmology, how will the universe end, and what is dark matter? So we've covered 2 of them, and then I'll change it after the stream to be like black holes. What would happen if you fire a laser beam while falling into a black hole? So if the universe continues undergoing accelerated expansion, eventually you would look out into the night sky and see absolutely nothing. If the universe's accelerated expansion is enough to be faster than the growing rate of the observable universe, which it seems to be, then eventually everything will be beyond our observable universe. So if you were to point a laser beam at those objects, it would never reach. Those objects are always going to be out of reach. And this is both very interesting and very slightly depressing, because a billion years from now, 5, 10, however many billion years into the future, it could be that the only thing you see in the night sky is our sun, and that's it, or not in the night sky, in the day sky. Even though everything could be flung so far apart that there's nothing left. But also, this is billions of years into the future. So not something we need to worry about. But yeah, we know how quickly the observable universe is growing. This is directly related to the age of the universe and the speed of light. These are things that we know. This gives us a limit on the observable universe. But the accelerated expansion means that there are objects that could be pushed away from our observable universe before their light ever reaches us. So it could be that the observable universe at some point becomes devoid of anything except us, at the center of our own observable universe, because things are going out too quickly, which is very, very cool. Okay, comment from Paul: sometimes we bring the dark energy. Love the joke, appreciate it, yes. I believe I'm the one who went into casually murdering people by throwing them in black holes and torturing people today, so that one's on me. Yeah, your question, Parth, was: if quarks can't exist in isolation, can they be generated as virtual particles? Yes, that's on my list. I'll get to it someday. Okay, comment from Scotty: I'm ready to ask the hard-hitting questions today, like how do lightsabers reflect blaster bolts if they're both just plasma? Yeah, they don't. But, sci-fi will allow it. We'll allow it. We can take issue with the midi-chlorians, but we can allow, lightsabers to be lightsabers. Okay. Hey, memes of destruction. Hi, welcome. Wondering if I know who you are based on that username, potentially. Anyway, hi, welcome to the stream. What's going on? We are talking about black holes and jumping into black holes, and could the universe be a black hole, and what would happen if you shoot a light blaster while falling into a black hole? On which direction should you shoot it to ensure maximum survival or maximum chance of people helping you escape the black hole? The conclusion was: don't jump into a black hole. And some casual Star Wars references, yes. So basically a regular day on Cup of Cosmology. Okay, so I think I might have answered all of the black hole questions. So I'm just going to scroll right to the top and come back to the bottom of the comments just to see if I have indeed covered all of the questions that have been asked, because there might have been some that I missed. So we're taking it from the top. There was discussion about keeping streams on Sundays. We all agreed that we're keeping the stream on Sunday. Yes. Then this whole conversation about black holes started because David Howden asked, do I recall that you can think of the whole universe as being a black hole? That was our jumping off point. That is what started this today. Okay, there was another question around the same time, I believe. Yes, there was a question from Lethargo about Mons. That's the one I wanted to get to as well. Okay, let me just read the question. You had a question about Mond. The background, my limited understanding, is that Mond tries to merge 2 equations for 2 regimes of gravitational strength. Isn't this an odd feature of a physics theory? Does it imply that if Mond was true, there would be 2 underlying mechanisms, not 1? So MOND is the idea of modified Newtonian dynamics. Okay, let me just put a pin in MOND, and I will check which other questions there are before jumping into MOND. I'm just gonna keep on going from the top and then go back to it. There was some discussion about politics as well that I ignored intentionally. Yes. Yeah, our borders are closed to all. Yeah, yeah, yeah. Okay, and there was another question that I did want to answer that I'm just going to write down. Okay, and I will get to that one in a sec because that was also a good question. Then we jump straight into black holes, and yes, I think all of the other questions we have potentially answered by now. Yes, I think then we got really into black holes. I think all of the black hole ones I answered. We can come back to those. Okay, so down to the bottom. Okay, yes. So I was recommended by the algorithm. Amazing. Welcome. Thank you for joining. So glad to see that you found us through the algorithm. Feel free to ask your questions. This is live. This is interactive. Any questions you have, nothing is off limits. Well, there are some questions I might not answer. Don't get too personal, but ask away, and I will do my best to kind of answer or answer the best I can. Yes. Yes, Latharga, you reminded me about Mons once I jumped back up, and now I've seen that you reminded me about Mon, but I already found the Mon question. Let's see. More questions coming down here. You had one, James. If it's the faster than light one, I've written it down. If it's another one, please feel free to ask it again because I didn't necessarily write that one down. Okay, so two questions I wanted to answer. I'm going to leave Mond for a minute and answer the other one because I mentioned multiple times that nothing can travel faster than light in a vacuum. And there was a question, I didn't write down who asked it, but there was a question of, does that mean we can travel faster than light in a non-vacuum? And the answer is absolutely yes. So light can be slowed down by different mediums. For an example, light traveling through air is going to travel slower than light traveling in a vacuum. Light traveling through water is going to travel slower. Light traveling through a very opaque and dense object like Mercury is going to travel extremely slowly to the point that you might not even see it come out the other side. You can absolutely slow down light with a medium. This is something that we do on a regular basis. We can slow down light in a medium. And this actually leads to fun things where you can get, if you have a medium of a specific density, you can slow down light enough that you get different flashes and light behaves in different ways when it slows down, which allows us to do different experiments. Oh, this was your question, James. Excellent. Great. I'm glad that was a question I found. Yes. So we can absolutely slow light down by using a different medium, and then it is possible for things to travel faster than light in that medium. For an example, if I have a bowl of mercury, light is not going to travel very quickly through that mercury if at all, but I can drop a stone in the mercury, which is going to slowly travel to the bottom. Um, the easiest way to see how we can slow down light is take a transparent bottle or a glass and shine a laser beam through it. Maybe not with water, fill it with something fun like honey or maple syrup or something like that, or treacle or something, and shine a laser beam through it. And you'll see that as the laser beam comes into the water, instead of being a straight line, it slightly changes its path. And this is due to the fact that light is going to travel differently through that medium. It's going to slow down, it is going to slightly distort, depending on the angle at which it comes in and fun things like that. And the refraction index, which is how much of the light you reflect and how much you absorb and how much you let through. So we can absolutely manipulate light in other mediums, and we can actually slow light down in medium. So then the question is, can we or any matter, follow up from Paul, can we or anything travel faster than light in the same medium that the light is traveling in? Absolutely. I think a clear example is something like Mercury, where you can have objects falling through Mercury, but Mercury is opaque because it slows down light so much. Also, if you wanted to go swimming in a swimming pool of mercury, probably don't do this. Like, I should add a health advisory, please don't swim in a swimming pool full of mercury, but you would be able to traverse it while light can't. So you are traveling faster than light in that medium. So whenever I say that nothing can travel faster than light, I specify in a vacuum because outside of a vacuum, you can slow light down. Light travels slower in air than in a vacuum. It travels slower in water than in air. So light can absolutely be slowed down, and then you could travel faster than light in water. You could travel fast. I mean, you'd have to run pretty fast, but hypothetically, it is possible. Whereas in a vacuum, light is the absolute limit of how fast could you be able to travel, and light is the limit of that. No matter what you do to your equations, in a vacuum, nothing will travel faster than light. However, once you're not in a vacuum, you can slow light down. A stone would float on the surface of Mercury. Okay, fine, take a stone made of iron. Take a big like metal ball and drop it in the Mercury. If it's denser than Mercury, it will fall through. And you could gradually push your way through Mercury if you wanted to. It would be difficult, but you could. But yes, you're right, Mito. If you take an average stone, it would sit on the surface of Mercury, it wouldn't fall through. But if you take something that's denser than Mercury, you can throw it through, whereas light wouldn't travel through as easily. But yes, you can absolutely slow things down. A comment from Lathargo here: isn't Cherenkov radiation related to light speed in a medium? Absolutely. And I love that you mentioned that, because that is kind of what I was implying just now when I said that if you have a very specific dense medium, you can slow light down enough to get cool effects. One of them is Cherenkov radiation, whereby you can basically track particles by getting them to travel through a medium that triggers specific decays in the particles and then trigger specific light showers. God, I hate the word light shower. I said light shower and immediately regretted it. You can have different light beams in different directions, and Cherenkov radiation is basically getting light to show up in a medium due to it traveling slower than you would expect. So that is something that you can absolutely do. Yes, and Cherenkov radiation is a way that we use to look for highly energetic particles that are crashing into the medium, producing light. The medium is dense enough that the light produces a cool, like, blue cone. In the same way that if you have a plane that breaks the sound speed, you get that kind of boom. The way you'd represent that boom traveling, there are pictures of the Concords or similar planes. When they break the sound barrier, you get the boom, but you also get kind of a cone around it, and that is the same idea as Cherenkov radiation, which is this radiation you produce, light that you produce when high energy particles come into a specific medium. It is very, very cool. Okay, more comments on this here. There was a comment from Paul here. Yes, traveling through medium the same speed as light or faster than light? Yes. Comment from Scott: I love how light slows down as density increases, but sound speeds up. I know it's because of the nature of compression waves, but it's still cool. Absolutely. So the way sound works is the closer the atoms are, the easier it is for sound to travel. Kind of like sound kind of needs a domino effect, where you need one atom to vibrate into the next one and so on. So the denser the medium, it depends. There are some medium that are insulating, but kind of the closer the atoms are, the easier it is for a pressure wave to move forward. Whereas for light, there's more atoms that can absorb or reflect the light, or distort the light, or deviate the light. So different ways that these things behave. Okay, question from Prathia. We've moved on to many more cool questions. I do in fact have the Mond question on my list. Don't worry, Mond is still coming. Question from Prathia: can X-rays and gamma rays be energetic enough to pass through Mercury? I don't know. Potentially, I'm not sure. This is a solvable equation. This is something that, to answer your question, I just need to know the refraction, like how dense Mercury is, the refraction index, or how much light it lets past. And then you could calculate that. Not a calculation I'm going to do now. It's a calculation I knew how to do during my undergrad in my optics course. I don't necessarily know how to do it now. But potentially, yeah, if your light is energetic enough, it could travel through certain mediums. That's kind of how we use X-rays to see through skin, right? Because X-rays are so cool. If you think about an X-ray machine, the way we kind of use highly energetic light to peer through our skin is insane. It's just like, I know how X-rays work, and I'm still always like, you have a highly energetic light, and it, you can see through me, huh? Why do I become translucent to X-rays? Why are my bones not? I know the answer. It's related to the density, and it's very, very cool. But also, when you stop and think about it, it's kind of like, yeah, physics is weird. Is there a sweet spot where sound travels faster than light? Absolutely. You can have a medium where you can have sound but no light. Yeah. I was about to say in a dark room, but that's you can just turn on the light. So that's not a fair example there. Question from John. Does the intergalactic medium slow down light significantly enough that it needs to be accounted for in cosmic scale observations? Very much depends on what is in the intergalactic medium, but the short answer is absolutely yes. Usually the intergalactic medium, the space between galaxies, the intergalactic medium, intergalaxy stuff, the stuff between galaxies is pretty empty, but there's also going to be hydrogen clouds. And hydrogen clouds have the thing that they can be ionized, they can absorb light and re-emit it. And this causes the light to have absorption and emission lines, and based on that, we can figure out things about the intergalactic medium. So while we don't need to take it into consideration on large scales, we do actually need to consider when you're looking at light coming from a distant galaxy, that light has experienced differences while traveling through the intergalactic medium. Not so much about it being slowed down, but more about it being absorbed and bounced around and re-emitted. Likewise, this happens to all light traveling inside the universe. So this is absolutely something that needs to be accounted for in cosmic scale observations. In fact, we can take this back. If we think about the oldest light we have in the universe, is this thing here, an hour and 22 minutes. That has got to be a new record. The CMB, the cosmic microwave background radiation. This is the oldest light you can see in the universe. This is the afterglow of the Big Bang itself. This is what the universe looked like 380,000 years after the end of inflation. What you can see here are the particles of light. So in the early universe, there were four main components. Dark matter was doing its own thing. Protons, electrons, and photons, particles of light, were bumping around into each other. As the universe gradually cooled down, the protons and the electrons could combine together to form the first neutral hydrogen. At this point, the photons can no longer interact with those things, so they break away and they start traveling freely throughout the universe. These photons have been traveling freely ever since. And yes, I am laughing at how I tied the CMB into this today. Took me a while, but it's here. So for anyone not familiar with the show, this image, my favorite thing in the universe, has to appear every single show, usually within the first few minutes. So we're on a record today, an hour and 22 minutes. So as the universe cooled down, protons, electrons combine together. The photons, the particles of light, break away. They have been traveling freely ever since. As they've been traveling throughout the universe, their redshift, their wavelength has stretched, which now puts them in the microwave range of the electromagnetic spectrum. So this is background light that you see in every direction you look, and it is microwave, so it is the cosmic microwave background radiation. The differences here, the orange and blue ones correspond to slightly more energetic or slightly less energetic photons, particles of light. And by looking at this figure, we can understand things like the components of the universe. The universe has dark matter, dark energy, normal matter. We know that the universe is 13.8 billion years old. The reason I'm showing this right now, because we were talking about the intergalactic medium. So the question was, does the intergalactic medium slow down light significantly enough that it needs to be accounted for? Basically, yes, because this light here from the CMB is going to be absorbed and emitted. It's going to experience changes due to the galaxies in the way. So when we look at this light, there is something we need to take into account, which is, has this light been absorbed or emitted by galaxies on its path towards us? Now, because the CMB is very low energy by now, it is much less likely to be absorbed or emitted than high energy photons, such as the ones coming from a distant galaxy, but you can still have these slight effects. So when we look at the CMB, there are tiny, tiny corrections we have to do to account for things like light being slowed down, usually more likely to be due to gravitational fields, but also it can be absorbed or emitted by the intergalactic medium, but not as frequently because it is much, much, much lower energy. Okay, thank you for giving me the chance to tie in the CMB there. That had to happen. Okay, where were we? We were talking about light being slowed down. And there was other questions that I need to get to as well. Where were we? Let's see. I went on a CMB tangent there. Whew, excellent questions. And we're getting to the 1 hour, 30-minute mark, and there are still multiple questions. So let's do some quick fire ones. I think even iron floats on water. Huh? You probably need tungsten. I guess on Mercury, yes. You'd need tungsten or osmium for the best results. Yes, you need something dense. You throw it in Mercury, it will sink eventually. Follow-up from John. In the CMB plasma, was sound faster than light? In the very early universe, yes. You had these kind of oscillations where you had sound waves and light kind of being tied into this early universe plasma. So technically, the sound waves were traveling faster than light in that CMB plasma. Absolutely, yes. Very, very, very excellent point there. Okay, comment from Scott. I guess most solids have sound propagation but are opaque. Exactly, yes. Are you saying the CMB is absorbed or emitted, or are you saying it can be absorbed or emitted? Emitted, as in absorbed and then emission. Absorption, emission. Not omission with an O, emission with an E. It is absorbed or emitted with an E, yes, by things in the way. So it gets absorbed and it also gets emitted. However, for CMB photons, this is less likely to happen because they are lower energy. So again, I jumped into the CMB here, but just to be clear that the intergalactic medium is much more likely to absorb or emit photons from background galaxies than the CMB itself, because the CMB is very low energy, but it can still happen. As to whether it's the same photon, that is an interesting question. Technically, photons are absorbed and emitted all the time. Does it change the photon? Is it still the same light? Is it still the same origin? It's an interesting question to ask. How do we define the identity of a photon? If a photon is emitted by a particle and absorbed and emitted by the same particle, is it still the same photon? Is it a different photon? How do we define that? Yes. Indeed, but in principle, the CMB can experience this kind of slowing down by the medium, but it is much bigger effect is kind of it slowing down due to the gravitational field rather than due to individual things in the medium absorbing and emitting it. But the intergalactic medium can absolutely slow down light coming from a distant galaxy. So I jumped into the CMB, but it's not necessarily a good example because while the CMB is moderately affected by the intergalactic medium, it is very small effect. However, light from a distant galaxy is absolutely slowed down by these intergalactic mediums. Okay, I think there were two more questions that I wanted to get to, one of them being the MOND one. I'm going to finish on the MOND one. And there was another question just before this, a few minutes ago. Okay, question from John here. Do you think there could be other explanations for the scale factor of the universe changing besides the physical distance between things changing? I mean, that is how we define the scale factor. The scale factor is kind of the way we define the acceleration of the universe, which is objects moving away from other objects. It's not really so much as objects moving away from other objects. It's more that space itself is expanding, so every object moves away from every other object. It's not about the motion of the objects. It's about space itself being stretched. Okay, let's go into MOND. You have 4 more associated questions. Save them for the next show. Absolutely, James. That is amazing. I feel like today's discussions have triggered a lot of really cool questions. When an electron absorbs question from Prathia, then MOND, then we wrap up. Quickfire question from Prath. When an electron absorbs a photon, does it become heavier from the photon's energy being converted to mass? I mean, it kind of absorbs and immediately emits it. Right? So if you have an atom and you have the different electron shells, simplistic view of an atom, you have the shells of electrons, what usually happens is you will absorb a photon and the electron will jump to a higher energy state, and then this electron will re-emit the photon and fall back to its default ground state. So it's not so much that the mass changes, but the energy of the electron changes. It jumps to a higher energy state, and then when it re-emits the photon, it falls back down to it. in the simplistic view of an atom with shells of electrons around it, like the nucleus and the shells of electrons, you can kind of imagine an electron, a photon comes in, the electron gets excited, it jumps up a level, and then it falls back to the level and emits the photon again. So at that point, is it the same photon? It excited the electron, de-excited it, it caused this bleep, but technically the photon has been absorbed and emitted. Is it still the same? Is it still the same photon? Good question. Yes. At which point does the photon even have an identity to any of us? Mond. Let's get on to Mond. Mond is the idea of modified Newtonian dynamics. So let me just, yes. So when we talk about the universe and how things behave, how things interact in the universe, we generally use general relativity. General relativity is the description of how gravity behaves on large scales. It is something that we use to talk about black holes. We use to talk about the whole evolution of space. And within this, we have the idea that the universe, within a universe governed by the standard model of cosmology and general relativity, we have a picture of the universe that has three main components. Everything you see, everything you're accustomed to, everything from me to my sleeping cute cats to the stars you see in the night sky, this is normal matter. Normal matter only accounts for 5% of the energy budget of the observable universe. There's another 26.2% in the form of dark matter. Dark matter is this weird type of matter that interacts gravitationally but doesn't interact with light. It doesn't interact electromagnetically, which means it is essentially invisible. And then we have a 68.9% in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe. And that's pretty much everything we know about dark energy. We don't even know if it's constant in time anymore. Now, this idea of these three main components is supported by a lot of different pieces of evidence. When we look at things close by, some of this evidence includes things like the way that stars move around galaxies. If we considered the way things move here on Earth, if you're on a merry-go-round or anything spinning, if you get further away from the center, you're going to move a bit slower. Coming from Prathia, you have to step away. Thank you for joining. Was great to see you here. It was great to have all your questions as usual. I've made comments on quark confinement and quark degeneracy. We'll come back to them someday. Thank you for joining, Prath. So, what we see when we look at nearby galaxies is that the stars close to the center of galaxies and the stars on the outskirts of galaxies orbit the galaxy with approximately the same speed. Whereas what we would expect from what we've understood of how forces work, how gravity works, is that the further you are away from the center, the slower you're going to move. And this is not what we see in nearby galaxies. One explanation is that galaxies are not just that central bulge, but actually a full halo of dark matter surrounding the galaxy, which is what is kind of dragging everything else around. Then we have things like the way galaxies smash together. When we look at how galaxies collide, the way the mass is distributed is not sufficient unless we add something like dark matter. Now, there's a lot of different pieces of evidence that support the idea of dark matter, ranging from how galaxies behave, how stars behave in galaxies, to the overall distribution of matter in the universe. So MOND, modified Newtonian dynamics, is the idea that maybe we don't need dark matter, maybe we just need to refine our theory of gravity on small scales. So I want to make clear that this is a subtype of modified gravity, but not all modified gravity is MOND. So modified gravity is the idea of modifying general relativity to account for things like dark matter or dark energy across the whole cosmic expansion, across the whole universe. MOND is a specific type of modified gravity that, rather than modifying general relativity, modifies the equations of gravity that we use on small scales, which is Newtonian gravity. When we talk about the motions of stars around a galaxy or the motion of our planet around the central star, we use Newtonian gravity. Basically, Einstein's general relativity in close environments simplifies or can be simplified to Newtonian gravity. When you don't have things like black holes at play, when you're just focusing on small systems like a planet system, a planetary system, or a galaxy, we use Newtonian physics. So MOND is the idea that on these scales where Newtonian physics applies, maybe we have a misunderstanding, and by accounting for this, we could explain the effects that we attribute to dark matter. So MOND is an alternative idea to dark matter. Now, MOND does kind of, because you can simplify general relativity to MOND in small scales, and MOND only focuses on this part of it, MOND doesn't really say much about general relativity, and the idea is on large scales, general relativity would still be valid, but on small scales, such as one planetary system or galaxies, we would need a modification of Newtonian dynamics according to MOND. Now, MOND, this modified Newtonian dynamics, can very successfully explain things like the motion of stars around galaxies. So if we just focus on that piece of evidence for dark matter, MOND is an equally good explanation. And then the question that people who research MOND ask is, why do we need to complicate things with a new species when we can just modify our existing laws? However, MOND so in that regards, MOND is a perfectly valid theory to explain the motions of stars around galaxies. However, that is not the only piece of evidence we have for dark matter. There is a lot of other evidence for dark matter. For an example, one of the biggest pieces of dark matter that we have is this thing here. This thing here, the cosmic microwave background radiation, again gives us a snapshot of what the universe looked like in its infancy. This picture, this cosmic microwave background radiation really does paint a picture of a universe that has 4.9% normal matter, 26.2% dark matter, and 68.9% dark energy. And trying to explain this picture without dark matter is extremely difficult. So I think the question was phrased along the lines of, is MOND kind of a valid theory, or not quite phrased like that, but does MOND make sense kind of thing? So purely in terms of how you build scientific theories, MOND is a perfectly valid scientific theory or model, more to the point, is a valid model to explain the motions of stars around the center of a galaxy. However, when you take all of the evidence that we have for dark matter, MOND can't explain it all. The argument that Mondians use is they're not trying to. MOND was conceived very much to explain things on scales of galaxies, so you can't really expect MOND to explain the cosmic microwave background radiation. However, that then means that if you think that MOND is the correct answer on small scales, you still need something else to explain why the CMB looks the way it does, why galaxy collisions look the way they do, and why the large-scale structure of the universe looks the way it does. So dark matter has kind of the advantage that it can explain all of these different things. Whereas if you want to modify gravity on local scales and say that the way that stars move around galaxies is explained by a modification of gravity, you do still need something else to explain all the other effects that we attribute to dark matter. So your question, which you just repeated here, thank you, Lothargo, was it having two regimes, and if that is weird and would imply multiple mechanisms. So in a sense, yes. If you just want to focus on the regime of local galaxies and how stars move in these local galaxies, then it is perfectly valid. You can use MOND to explain this, but then you would need a different mechanism or a different thing to explain, for an example, why the CMB looks the way it does, or why the large-scale structure of the universe looks the way it does. So in a sense, if you accept MOND for local explanation, or for an explanation of the local effects that we attribute to dark matter, it is not sufficient to explain all the other effects. So in that sense, it's not really odd as a theory. It's just that it's very good at doing the thing it was designed to do, which is local, small scales. It can't offer a broader picture of how dark matter behaves across all scales because it's not the way it was designed to do so. In that sense, it is a perfectly valid model to explain one effect. However, dark matter is a very good model to explain multiple effects. And therefore, the general consensus is that dark matter is a better explanation to all of these effects. But there is not necessarily a given reason why we need one thing to explain all of these effects. But as your question is kind of implying here, if you believe that MOND is the correct answer for this phenomena on small scales, you do need another mechanism to explain everything else. Dark matter, on the other hand, does offer this. Of course, there are some issues with dark matter. There are some slight things that we have not necessarily resolved. But when you take the broader picture, dark matter provides a better explanation. However, MOND is a perfectly valid model for the one thing it was designed to do. That's the thing it does very well, because that's what it was kind of designed to do. So I think it's very, very valid to look for alternatives to dark matter. Personally, I would like any dark matter or dark matter alternative, in my mind, should be able to explain the CMB, because that is one of the biggest pieces of evidence we have for this type of non-visible dark matter, or a type of matter that interacts gravitationally but not visibly. So yes, MOND is not odd as a theory. It is a perfectly valid model to do exactly what it was designed to do, but you can't ask it to do more than that. However, dark matter can do a bit more than that because it's a more global explanation. Excellent question about MOND, and it is a very good thing to talk about as well. Whew, okay, we have been going for 1 hour and 40 minutes. This is a very long stream. My tea's long gone, my water's almost gone. This has been super, super, super fun. I've really enjoyed the questions today and the discussions, and we spent most of the stream talking about black holes, but in a way that we don't often do, because black holes is a topic that comes up often in these streams. But I loved the angle we were going with it today, of like falling into a black hole and the different light effects and Hawking radiation. It lets me talk about different aspects of general relativity, which is really, really cool. Time does indeed fly when we're having fun or orbiting near a black hole, and I do have my black hole plushie. So yes, that's why we have longer streams, because this guy is causing time dilation. But then there's also this one who would be counterbalancing it. So let's not focus on the white hole. We just have a black hole. Yes, this has been super, super fun. Thank you, everyone, for joining and for engaging, for having these conversations, for asking these questions, for chatting amongst yourselves. It's been really fun. Paul is saying you're saying thank you to the cats for lending me. Yeah, I fed the cats before the stream, and now they're sleeping, because the trick to do the streams is to make sure the cats are fed before I jump on. Otherwise they would have stopped me long ago. Okay, this has been super, super fun, everyone. Thank you so much for joining. As I said at the beginning, I've been on a break for the last 4 or 5 weeks, and I know it would be very easy to kind of lose focus and not come back. So I love that even when I take an extended break, you will come back. You will hear great questions, brilliant conversations. It's so much fun. It's nice. It's kind of reassuring for me to know that I can take a break if I need to, and you will all still be here when I come back. So thank you for that. Cup of Cosmology should potentially be online next Sunday. But there is a 2-day event. I'm not yet sure if I'm going to both days, but if I go to both days, then I will not be online next Sunday. If I only go on the Saturday, I will try to be online next Sunday. Let's say that Cup of Cosmology should be back next Sunday, but with a caveat, maybe, to be determined, TBD. Make sure you subscribe to the channel and you'll be notified before I go live, then you'll never miss a stream. If Cup of Cosmology is online, it will be the same time as always, which is 8 p.m. in Finland on a Sunday, 7 p.m. if you're in mainland Europe, 1 p.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast of the US. As always, there is a time zone converter on cupofcosmology.com where you can figure out when the next stream is in your own time zone, so you don't miss it. As said, Cup of Cosmology should be back online again in next week. Thank you, everyone, for the questions. Thanks for the comments. It's been super, super fun today. Really great to have you all here. Hope to see you again in the next stream, whenever that may be. And I hope in the meantime, you will take care of each other and stay curious.